All right, two more similarity theorems to talk about here, and then we can wrap that up. So next triangle similarity theorem that exists is the angle-angle similarity theorem. And the angle-angle similarity theorem for triangles says that if two angles of one triangle are congruent to two angles of another, then we can say the triangles are similar. And this comes from the fact that if you change the size of a figure, the angles of the figure do not change. They remain congruent to each other. So that's where this congruent comes from. It doesn't mean the triangles are congruent. It means that the angles are. And if the angles are, then the triangles are similar. So as a result of this, I have three more triangles on the screen here. Two of these triangles are congruent. Might be pretty straightforward as to which ones are. It's the two triangles that have two congruent angles. So we have 32 and 27. That's not 32 and 27. This one is 32 and 27. So we can conclude that these two triangles are similar. They're similar. They're probably different sizes. They could be different sizes. They could be congruent too. But they are definitely similar because their angle measures are exactly the same. Now, one thing to note here is that we don't have this third measure. So I just said that if figures are similar, all of their angles have to be congruent. Well, the reason why we only need two for triangles is because if we know two angles in a triangle, we can find out the other angle because the three angles have to add up to 180. So we can find the value of the missing side length, missing angle here, and that has to be the same as this missing angle measure as well. So we only need two angles in triangles to be congruent to conclude that they are indeed similar. Another one, the last one, is the side angle side similarity theorem that says if in two triangles the ratios of two pairs of corresponding sides are equal and the included angles are congruent, then the triangles are similar. So it's kind of a mouthful there. And what it's saying here is that the ratios of two pairs of corresponding sides are equal. Basically means that the corresponding sides are proportional and the included angles are congruent. What it means by congruent or included angles is that the known angle is formed by the two known sides. So notice that's what I have with these three triangles here. Here's the angle, and this angle here is formed by a known side and a known side. And when I say a known side, I mean there's a measurement on that side. So 32, it's formed by 6 and 11. 32 is formed by 9 and 14. 32 is formed by 16.5 and 9. So that's what this included angles means. And the included angles have to be congruent. So I made 32 the same in all of these. They have to be congruent, but only two of these triangles are similar because now we have to take a look at the side lengths and make sure that the side lengths are proportional, that there is a multiplicative relationship between those side lengths that's the same between the two. So we have 6 to 11. 6 to 11 from 6 to 9, 11 to 14. So I would map 6 to 9 because it's the shorter side, 11 to 14 because it's the longer side. 6 times 1.5 is 9, and I can find that by doing 9 divided by 6. 11 times 1.5 is not 14. So these two triangles here cannot be proportional because the multiplicative relationship between 6 to 9 is not the same as the relationship of 11 to 14. There's a difference there. So these two cannot be proportional. So it could either be the first and the last or the second and third. But let's think about what I just said. 6 times 1.5 is 9. So there's a 9 right there. 11 times 1.5 is 16.5. There it is right there. So the relationship or the ratio of similitude or the magnitude of the transformation or the scale factor between this first triangle and the last triangle is 1.5. These two triangles here have to be similar because the two pairs of corresponding sides are equal. In other words, 6 over 11 is the same as 9 over 16.5. And the included angles formed by those two sides are congruent. It's 32 and 32. So that's the side angle side similarity theorem for triangles. A couple of examples that illustrate this a little bit. First one is their classic sun shining and forming a shadow with a cactus and a meter stick. Usually it's a flagpole and a person. We've seen all this sorts of stuff before. Let's say if a meter stick casts an 80 centimeter long shadow. So that's this thing right here. That's 80 centimeters long. At the same time that a cactus casts a shadow 15 meters long. So this shadow right here is 15 meters. How tall is the cactus? Now this is working under the assumption that the sun rays come down here and that the cactus and the meter stick are parallel. So we're forming congruent triangles is essentially what's happening here. So to illustrate that, there's one of the triangles. Here's the meter stick. This length right here is the shadow, which is right there. And then this hypotenuse here is going to be the sun kind of, or the sun rays kind of coming over the meter stick there. And we're assuming also here that the meter stick is perpendicular to the ground. So we're assuming that's a right angle. What this looks like with the cactus is this. We have a 15 meter shadow. The height of the cactus, we don't know because we're asked to find out how tall the cactus is. And then we have this hypotenuse here. And we can assume that these two angles are the same because of the angle of the sun. So what we have here are similar triangles, and we know that they're similar because they have two angles that are the same measure. Those two angles are exactly the same measure. So therefore, these two triangles have to be similar. So in this case, what happens is we have this proportional relationship that 1500 divided by 80 has to be the same thing as x over 100. Now, where do these numbers come from? Let's talk about this because this is not very clear. 1500, where's 1500 come from? 1500 comes from 15 meters. I changed 15 meters to 1500 because this is in centimeters, 80 centimeters. So I have to change everything to the same units. Can't mix and match units here. I want to be making sure that I'm using the same units across this problem. So 1500 centimeters is 15 meters. And the 1500 corresponds to the 80. So 15 to 80, it's the length of the two shadows. So 1500 over 80, this ratio has to be the same thing as the ratio of the heights. So we have the length of the shadow of the cactus, length of the shadow of the meter stick, has to be the same relationship as the height of the cactus over the height of the meter stick. And notice I have this 100. Why is it 100? Because it's measured in meters. There are 100 centimeters in a meter. So to solve this proportion, whole bunch of ways we can do this. You can find out what you multiply 80 by to get to 100 and do the same thing to 1500. I'm going to use cross multiplication, means extremes property. Probably heard many different things for that. And what this just says is that I get 150,000 has to be equal to 80x. Where do I get this from? 1500 times 100 is 150,000. That has to be equal to 80 times x. That's cross multiplication, means extremes. Not the only way to solve this problem, but a way to solve this problem. And then I solve for x. Divide both sides by 80. If I divide both sides by 80, I get 1,875. And remember, this is in centimeters. So how tall is the cactus? Well, it's going to be 1,875 centimeters, or about 19 meters high, because 1,875 centimeters is almost 19 meters. So that's how we solve those problems in terms of similar triangles with respect to two angles, knowing they're the same, setting up the proportions and the ratio, setting up the ratios equivalent to represent a proportion, and solving for a missing value there. One more example here. Suppose that we're given a diagram and that WT and line segment UV intersect X with right angles as indicated. And we want to name the theorem that proves that the pair of triangles, this triangle right here and this triangle right here, are similar and provide a similarity statement. So first thing I'm going to notice here is since these lines intersect, what we have formed here are vertical angles. The first thing that I'm going to say is that angle TXU is this angle right here. Because if I call TXU, the angle that I'm forming, TXU, is right here. This angle is congruent to angle VXW. VXW is this angle right here, VXW. I'm forming that angle there when I say VXW. These angles have to be congruent. Why are they congruent? Because of the vertical angles theorem. If they're vertical angles, then they have to be congruent. So these two are congruent. Then as a result of that, the triangles, this bottom triangle and the top triangle, have to be congruent, or similar, I'm sorry, they have to be similar because they have two angles in them that are congruent. So they are similar by the angle-angle triangle similarity theorem. So this triangle down here has to be congruent to this triangle up here. Now we can't just say this triangle, that triangle. We got to be a little bit more specific. We got to use names. We got to call it TXU, XUT, UTX, whatever we want, VXW, so on and so forth. But we can't just throw those letters together and say that they're similar. We need to make sure that in our similarity statement, the corresponding parts match. So when I take a look at T, when I talk about T in this triangle on the bottom, what does that correspond to in the upper triangle? Does it correspond to this angle right here? Does it correspond to V? Does it correspond to W? If I look at this one, I don't know the measure of that one. T would not correspond to this right angle because we know that's a right angle. T's not a right angle. T wouldn't correspond to this angle right here because we know that that has to be corresponding to this because they're congruent. So T corresponds to W. As a result, V is going to correspond to U. V corresponds to U. That might be a little bit more clear because they're both right angles. And then this angle right here, which we're going to call TXU, as I called it right here, has to correspond to VXW. Right there, this angle right here, that's what I'm calling that angle. So we need to make sure those things match in our similarity statement. So U corresponds to V, so U and V I'm putting first. Angle X, right here, corresponds to angle X, of course. And then angle T corresponds to W, T and W. So the similarity statement is triangle UXT is similar, that means similar, to triangle VXW.